Hello and welcome back to the lecture on applied econometrics. We are into the third week of our lecture.
So we have been talking about normal distribution, and normal distribution is one of the distribution that is one of the most important distribution that we see in nature, and that is basically widely used in statistics and econometrics. Now, in this lecture, we are going to see the empirical side of it. We are going to use numbers. We are going to try to we're trying to make sense of the normal distribution with numbers. Now, to do that, we remember that we actually used something called Z. We used something called this this part we called as Z, right? And we substituted that Z and we got this formula. Now, the point here is, what is this Z? What is this Z and why it is important? So we define Z as Z is equal to X minus mu by sigma. Now, if I try to understand the Z using the normal distribution curve, so it would mean, let me actually have, let's say this is the mean, the mu. So this is mu. Use a different color. This is mu. And let's say I have my x, which is here. X is, let's say, here. And I have a sigma s, let's say. S is here, let's say. Sigma is here. Now, when I subtract mu from x, so what I get is this difference. When I subtract mu from x, I get this difference. Now, when I divide this difference with sigma, so basically I see how many standard deviation away x is from mu. That's basically the definition. When I do x minus mu by sigma, it shows how many standard deviation away x is from mu. Okay, so if let's say this is, this distance is 2 sigma, so then z is basically 2, which means that z is 2 standard deviation away from the mean mu. Okay, so that's basically the idea. Now, if I have my mu shifted, let's say mu is 0 here, and I want to substitute mu is equal to, let's say, 10, and then if I substitute mu as 10, so in the number line, so the normal distribution will shift. Let's say here, of course, they're not, I couldn't draw them equally, but let's say they're equal, and this is my new mu here, and mu is equal to 10 here, mu is equal to 10 here. And I can also shift it towards the left, and I can perhaps, let's say, mu is equal to minus 10, and it will shift like, oh, that's very bad. It will shift to the left. Let's say mu is equal to minus 10 here, and the normal distribution would be symmetrical around mu. Okay, so this is how we actually can construe the shift of normal distribution if we change the value of mu. Let's say let's try to understand what happens if we change the value of sigma. So if sigma is high, so which means the dispersion of the standard deviation is high, what happens is that the normal distribution gets wider. Normal distribution gets wider. So that is not really a very highly expected scenario where the sigma is high. For a sigma high, we will have the normal distribution something like very flat sort of normal distribution. Right? We don't want that kind of distribution. If sigma is low, we have a narrow sort of normal distribution. So all the observations are close to mu, and this is kind of a desired distribution because we want our x's to be close to mu, not to be very far away from the mu. In this case, all the x's are quite far away from the mu, and possibility of we will actually end up on it's difficult to actually detect the sigma, the mu from all these different dispersed observations, but whereas it is easier here. Okay, so so what happens is that irrespective of whatever the value of sigma is, it is big or small, what happens is that we will see that the normal distribution is actually the area under the normal curve. The area under the normal curve has some sort of relationship area under the normal curve is related to sigma. Okay, so irrespective of the value of sigma, whatever be the value of sigma, it really does not matter. The area of the normal curve will have some relationship with sigma, and we'll come to that, and we call that as 68, 95, and 99.7 rule. Okay, so this is the rule. We'll just talk about this rule, but before that, let us talk about something a little more fundamental, and that is basically how we understand the area under the normal curve, how we actually obtain the area under the normal curve. And to do that, we have to sort of again go back to our previous lectures where we actually talked about distribution cumulative distribution function. Okay, cumulative distribution function, CDF. So when we talked about CDF, it's basically you sort of when you talk about cumulative, so you basically add up all the probability densities that we have, and you get the cumulative distribution function. And let me actually explain how we sort of do that. So let's say this is the normal distribution curve, and I want to, let's say, this is my A and this is my B, let's say. And if I want to get the CDF up to the point A, so essentially from the left side, I basically add up this area under this curve from minus infinity up to A. Okay, so this is how I get the area under the curve. If I say, the area under the curve, for x is equal to A. So anything less than A would be considered under the when I consider the cumulative distribution function. But whereas if I say, cumulative distribution function, you want to estimate the area under the curve up to the point B, so you take minus infinity to B. Okay. Now, what do you do when you have to sort of get the area between A and B? So it's simple. It's simple. Basically, what you do is you do from minus infinity to A fx dx, and you basically subtract minus infinity to b fx dx, right? So basically, you take two cumulative distribution functions, and you sort of subtract these two, and basically the same cumulative distribution function across two different ranges, and you subtract these two to get the area under this curve. So depending on what range you want, so you basically define that way. Okay. Now, actually, if you remember the formula we derived, so fx in our case is basically 1 by root over 2 pi sigma square E z square. Okay. Now, if I substitute this fx here, and if I try to integrate this fx over this range, so it is a little difficult because the function is not really a very easy form of function. So that is something difficult of course, but there are some easy way out. And the easy way out is that basically that the z value that we have seen here, and the z value where we use this z, and there are certain standard formula or standard rules that we already have, and that is the area under the curve will actually depend on the standard deviation irrespective of their value. So let's say if the area under the if I take a standard deviation is equal to, say, one standard deviation away, so if my normal distribution is like this, and if I take one standard deviation away in both left and right, so this basically covers 68% of the area. Okay, so sigma, and if I take two standard deviation, so it is going to be, two standard deviation is going to be 95%. So that is basically two standard deviation on the left, two standard deviation on the right. And if I take three standard deviation, so it is going to be, so three standard deviation left, two standard deviation right, it is going to be 3 sigma, it is going to be 99.7%. So basically, if you take 3 standard deviation on both the sides of mu, then you are actually your the area under the curve is actually 99.7% basically of the entire area. So which would mean that only this little part, let me use a different color, only this little part you are leaving out here, only this little part goes up to infinity, and here only up to this little part goes up to infinity. So which would mean that consists like the rest of the area, which is 0.3%. Okay. So now using this, you can actually solve many problems. Of course, there could be, you can also have, not necessarily it has to be 1 sigma, 2 sigma, 3 sigma. And in those cases, we can use the standard normal table, this is the Z table. But let's see how things are easier if I have this formula, 1 sigma, 2 sigma, 3 sigma, and if we have the standard area known to us, okay? So we'll try to solve some problems, okay? Um, so let us do one problem. Let us do one problem. So let's say that let's say you have your mu is equal to 5, let's say, and you have your x for a given value of x, let's say 10, and you have your, let's say, SD or sigma is equal to 2.5. So I have chosen this number conveniently so that I don't have to use any calculator or any Z table. So now if I use if I get a Z, so x minus mu by sigma would give me, so 10 minus 5 by 2.5, which is equal to 2, right? My Z is equal to 2. So I get the sigma, and then of course I know if my sigma is 2, so like if my Z is 2, so how how much area this X would be covering. Okay, so I know that my sigma is, so let's say this is 5 mu, and this is X is 10, and sigma is 2.5. So basically, if I take 1 sigma away, so this is going to be 7.5, and this is 10. So essentially, Z2 means it is 2 standard deviation I'm talking about. So this area is actually 2 standard deviation area. So if this is 2 standard deviation area, and I know from my rule that this whole, if I have 2 standard deviation on both the sides, so that would have been 95%. Okay. Now here what I have 2 standard deviation on one side, 2 standard deviation on one side, and then on the entire side, on the entire this side, 50% of the curve is on the other side. So if I divide this, so for this part is going to be 95 by 2. This part is going to be 95 by 2, which is 47.5%, and this part is going to be 50%, other half of the normal distribution. So if I say any number, let's say if I have to get a probability of x less than equal to 10, any value, for any value of x which is less than 10, so that means any value of x which is this side, so that would mean the entire area, entire 50%, and this part, so which is 50 plus 47.5, which is total is going to be 97.5%. Okay, so this is how we basically, our life becomes easy when you know the area under the curve. Okay, so let us do another problem. And let's say the problem is, let's say we are actually measuring the height of children, and let's say the average height of children, let's say, is, let's say, 3 feet. Okay, 3 feet, and we have a SD of sigma is equal to, let's say, 1.2 feet. 1.2 feet. Now, if I want to sort of get, let's say, I want to know probability of x, let's say, greater than is equal to 5.4, probability of x x less than 1.8, and probability x greater than 6.6. So I will give this task for you to solve it. So I'll just give you the hint. So here what is happening is that you have, if I'm asking about x greater than 5.4, okay, so that means if I add 3, so this is a mean value, and if I add 2 standard deviation, 2 sigma, so that will be 5.4. So this is my mu, this is my 2 sigma, and this is basically going to be the area here. I need to know the area here. So here it is 50%, and here we have already seen in the previous example, this is 47.5%. So what is the rest of the area? So that is basically the answer. Okay, so that's quite obvious. Here, if x is less than 1.8, again, like 3, so you have the 3 is mean, and then if you subtract 1 sigma, so this area is basically your answer. Okay, so this area is basically answer. Now we know that so basically if we have 2 standard deviation, 1 standard deviation on both sides, so that is 68%. So this part is going to be, for the second problem, this part is going to be 34%, and here this one is going to be 50%. So if I add this 2 and subtract, so whatever is left is the answer. Okay, so that is basically 16%. What about the third one? So third one is I actually have 3 sigma. So x has to be more than 3 sigma. So it has to be here. Okay, it has to be here. So I know up to 3 sigma, this area is 99.7%. And I asked for only this area. Okay, so rest 0.3% is actually is basically covering both these areas. So I don't need this. So I only need this because I'm only concerned about the heights which are above 6 and 6.6 feet, and that is going to be, so basically 100% minus 99.7 by 2, which is basically 0.15%. Okay. Okay, so we are, I think, pretty much now clear about this. I'm going to show you. I'm going to show you some. I'm going to show you some Excel sheet here. Okay, and this is basically, I'll just show what is a probability distribution function, probability or density function, and then cumulative distribution function, and how we can derive the normal distribution curve from here. So let me actually just write down some numbers. So let's say I start from minus 10, minus 9, minus 8, and so forth. And let me actually get all the numbers in this way. Minus 2. So let me get at least 20 numbers. So if I just continue with this, so I'm going to get 8, let's say I get up to 10, let's say. Oops. So I get from minus 10 to plus 10, and let's say I have a mean is equal to, mean is 5, mean is, let's say, okay, we can keep mean is 5, and sigma is 4, let's say. Okay. So now when I have to get a PDF, so basically we use a function called norm dist. Norm dist. So for norm dist, I have to, if for a probability density function, I have to give the value of this. The average is 5. So since I want it to be constant across all the values, so it is going to be dollar signs, and then oops, here the norm dist, the number is going to be this, the average is going to be this, and we put $2 signs, and then we have the standard deviation, which is this, and again we put $2 signs because we want it to be constant. And the form type is important because form type is talking about whether I want a probability density function or cumulative form. So let's say I want probability density function, so which basically means I'll get the height. So I have to close it, I guess. What happened? Test. So here is a value, and then I sort of then I sort of use the formula for all the cells and get the values. So here I got the values here. So these are basically the PDF. Okay, these are PDF. This norm list is actually giving me a PDF. So this particular form of norm list is giving me a PDF. Now I get a CDF, cumulative density function, and the same thing. Let's say this is equal to this. Oh, no, let me just not do that. So I'll just use the same norm list, and then I'll use the number. Then I'll have the mean. Norm list. So now I'll use the number. Number is this, and the average I will use this. The mean. Now I have to put a dollar sign. Just fixing the cell. The standard deviation is going to be this. Then I have to put a dollar sign before 4 and before A. And for the form type, I need to use the cumulative form, and then I press it. So basically, I am getting a cumulative, all the values from minus infinity to minus 10 are being added up when I'm using a cumulative form. Okay, so let's see. So it should ideally give me as 0.5 at some point. At 5, I guess I will get 0.5 because it has to be symmetrical around 5. So here I get 5, and then if I keep sort of I get other values. So now if I, let's say if I actually plot this, if you actually you can have an interesting thing. If I make it 0, so you see the mean has come to 0. The mean value is, the CDF is 0.5 at 0. Basically that makes sense because the normal distribution is symmetrical around 0. Now if I plot a normal distribution curve, I can actually take the different values, of the PDF values, and at the same time we can take different values of the CDF. So for PDF, I will see the normal distribution curve, whereas for CDF, I'll see something like the CDF. Let me actually draw it. For PDF, I'm going to, if I plot the PDF, I'll get something like the normal distribution. But if I plot the CDF, I'm going to see something like this. The sum total of all the probabilities will be represented by the cumulative distribution function. So I will not do it here, and I would ask you to do it on your own. Get some imaginary numbers, plot some numbers, and play with the value of SD, value of mean, and of course use the norm dist function to see how the normal distribution is changing its shape, and basically with the value of mean and standard deviation. So with this, we kind of end this lecture, and a couple of other distributions we'll cover in the next couple of lectures.
With this, we end the lecture here. Thank you.